So today I want to look at some ionization energy trends, namely like how much energy it takes to remove successive electrons, more than one electrons. So let's take a look at magnesium. So magnesium has this electron configuration. The first ionization energy is how much energy it takes to remove that outermost electron. So we're talking about this one right here. So in this case right here, you have 12 protons, 12 electrons. So to remove that electron, it's about 735 kilojoules. So to remove this electron right here, 735 kilojoules. So I'm going to erase it. So now that electron is removed. That's the first ionization energy. The second one is to remove a second electron. So it's to remove this one right here. Now in this case, what happens, I still have 12 protons, but only 11 electrons. So the Z effective increases. So the Z effective has increased. So in this case, it's going to take more energy. In fact, it takes about 1,445 kilojoules of energy. So as Z effective increases, ionization energy is going to increase. Now, after I remove this one, magnesium has a full valence shell, has a full energy level. So this is like the octet rule. That second energy level is full. It's kind of like a noble gas, which have full energy levels. Now it makes it very, very difficult to remove that electron right there. You can remove any of those P's, they're all the same. And so in this case, it jumps up a lot. In fact, when you do that, let me take a look. It jumps up to 730 kilojoules. So you're talking 7 times higher now because you have this full valence shell. So whenever you're trying to remove an electron from a full valence shell, so 2s2, 2p6, electrons don't like to be removed because that's a very stable molecule or atom in this case. So the electron ionization energy is going to increase a lot. Let's take a look at aluminum, and then we're going to see a trend in which once I start removing electrons from the 2p6, the ionization energy really increases. So in this case right here, the first ionization energy, I'm removing an electron from a 3p, and that takes about, I think I wrote it down, 578 kilojoules. At this point right here, aluminum has 13 protons and 13 electrons. I removed that electron. Now I have 13 protons and 12 electrons. So this one is gone. To remove this other electron for the second ionization energy, so again, you talked about successive electrons, it's going to be more energy because the Z effective increase. Same number of protons, but less electrons. In that case, it goes to 1,817. So it went up about 3 times, and the reason is I remove an electron from a full s orbital. That actually increases it a little bit more. This is gone. Now I have 13 protons and 11 electrons. So again, now to remove this one, it's going to be more energy. So Z effective always increases the more electrons you're removing from that. So that's going to be 2745. So that's gone. Now I want to remove this one. So this is like magnesium now. I've got to the point now I have a full valence shell. It makes it very stable, makes it very difficult to remove an electron. So even though, or it's 2 factors, so it has 13 protons and 10 electrons, the fact that I'm removing it from a full valence shell makes it even higher. So in this case now, it's like 11,577 kilojoules. So it goes up about 6 times between removing this one as opposed to this one. So the main thing is to note that if I remove an electron from a full valence shell, it really increases the ionization energy. So for aluminum, it had to go to the 4th electron to be removed. For magnesium, it was like the 3rd electron to be removed.